All right, so this is chapter 19 over high altitude and its effects on the cardiopulmonary system. My name is Patricia Bazil, and my group members Isaac Addison and Dylan Lemuc will also be presenting. So the objectives of chapter 19, the first one is to describe the effects of how high altitude on affects the cardiopulmonary system. The other is to describe other physiological changes caused by high altitude. So, effects of high altitude on the cardiopulmonary system. Nearly 30 million people live at altitudes greater than 80,000 feet. This includes mostly the Rocky Mountains of North America, the Andes Mountain of South America, the Himalaya Mountains of South Central Asia, and the Ethiopian highlands of East Africa. Many lowlanders visit high altitudes for work or recreation, but short term exposure can lead to altitude sickness. Under normal conditions, barometric pressure and PO2 will progressively decrease with altitude. Altitude of 18,000 to 19,000 feet usually has a barometric pressure of half the sea level at 760 millimeters of mercury. Altitude of 29,028 feet, which is about the height of Mount Everest, usually has a barometric pressure of about 250 millimeters of mercury. And altitude of 65,000 feet usually has a barometric pressure which falls below the pressure of water vapor and where tissue fluids begin to boil. Ascending above Earth's surface means barometric pressure progressively decreases and the atmospheric pressure declines. As the atmospheric pressure decreases, the individual's arterial oxygen pressure also decreases, as you can see here with this table pulled from the book. Acclimatization. So, acclimatization is when an individual who usually lives at sea level spends a period of time at high altitudes.
August 22nd. Oh, sorry.
Sorry, what happened? Okay. Let me get out of here and go back. Okay. So again, acclimatization is when an individual who usually lives at sea level spends a period of time at high altitudes. This kind of causes them to develop compensatory responses. After a period of acclimatization, though, an individual may reach the summit of Mount Everest without supplemental oxygen. So basically, what this means is after a period of time, an individual who has kind of been acclimatized to the higher altitudes may reach the higher altitudes, such as Mount Everest, without supplemental oxygen. Sudden exposure to oxygen tension leaves an individual at a state of consciousness. So, what this is saying is basically that someone who has just been exposed to high altitudes kind of may pass out or kind of experience a state of unconsciousness. So, ventilation. A prominent feature of acclimatization is increased alveolar function. As mentioned in slide 3, atmospheric pressure decreases, which also means that arterial oxygen pressure will decrease. Arterial oxygen will eventually decrease low enough to about 60 millimeters of mercury to stimulate carotid and aortic bodies known collectively as peripheral chemoreceptors. And as you can see here, this image was pulled from chapter 9. This is basically showing the aortic and carotid bodies or the peripheral chemoreceptors. Since peripheral chemoreceptors don't adjust to low oxygen levels, increased breathing continues as long as the person stays at high altitudes. So, moving along to pulmonary function and mechanics, when chemoreceptors are stimulated, they transmit signals to the medulla to increase ventilation, a process called hypoxic ventilator response. Hypoxic exposure contributes to vital capacity decrease within 24 hours. It is believed the causes of the reduced vital capacity includes increased interstitial lung fluid, which in turn results in airway narrowing, air trapping, and delayed emptying of alveolar gas. Long-term high altitude residents tend to have an increased vital capacity size Individuals born in higher altitudes tend to have the largest vital capacity. So, unlike individuals exposed acute hypoxic environments, long-term high altitude residents have an increased vital capacity, and people born and raised at higher altitudes develop larger vital capacities than those who just reside there and have resided there for a while. So, polycythemia. So, polycythemia is basically prolonged low oxygen levels that stimulate erythropoietin to increase red blood cell production in the bone marrow. So the increased hemoglobin available in polycythemia is an adaptive mechanism that increases the oxygen carrying capacity of the blood. And in one of the previous slides, I have a picture of kind of how polycythemia works. So yeah, I would just refer to that picture. Individuals who live at high altitudes often have a normal or even above normal oxygen carrying capacity. This is despite a chronically low PaO2 and oxygen saturation. In lowlanders at high altitudes, red blood cell production rises for about 6 weeks before stabilizing, while plasma volume decreases. So this basically means that there's no significant change in the total circulating blood volume. So after 6 weeks, an average hemoglobin concentration of about 20.5 grams per deciliter has been observed in mountain climbers who climb to altitudes greater than 18,000 feet. Acid-base status. So increased ventilation from peripheral chemoreceptors at high altitudes lowers PaCO2, leading to respiratory alkalosis. Over a 24 to 48-hour period, the renal system tries to offset the respiratory alkalosis by eliminating some of the excess bicarbonate. But despite this, mild respiratory alkalosis usually persists even in high altitude natives, so people who are very used to being in high altitudes. The alkalosis enhances the loading of oxygen to the hemoglobin as desaturated blood passes through the alveolar capillary system. It is also argued, however, that the increased affinity interferes with the unloading of oxygen at the cells. Studies show that higher oxygen affinity at high altitudes is helpful. This is backed by the fact that mild respiratory alkalosis often remains in mountain climbers, high altitude natives, and animals in low oxygen environments, even after the kidneys have had time to adjust. And as you can see here, the picture kind of just shows you what an individual would go through while dealing with respiratory alkalosis.
Okay, now we're going to go to alveolar ventilation. Now, we've seen that normally oxygen will fully equilibrate in the lungs. However, accounting for higher altitudes, oxygen does have difficulty diffusing across the alveolar capillary membrane, which will lead to an increased difference between the alveolar and arterial oxygen tension. Now, at higher altitudes, we know that oxygen transfer will not be complete. We can use Mount Everest as we have used as an example within the previous slides. At 29,000 feet up in the air, at higher altitudes in general, only about 80% of the available alveolar oxygen actually moves across the alveolar capillary membrane and reaches the blood. So about 20% of the available alveolar oxygen doesn't actually reach the alveolar capillary membrane and the blood. But we know that diffusion is further increased with exercise and within individuals with interstitial lung diseases. Next slide. Now, this is just a representation of the alveolar ventilation. Now, on the left side, we have alveolar ventilation under normal conditions at normal sea level, and then we have the one on the right with higher altitude levels. So what we can see on the left side under normal conditions is that it takes about 0.25 seconds to reach for the blood to reach equilibrium, and then it takes about 3 times the time for higher altitudes. So we know that it takes a longer bit of time for the blood to reach equilibrium. Next slide. Now, we can explore the realities of high altitudes. These are an array of facts that we know based off of what high altitudes can do for your body. So at high altitudes, we know that breathing and heart rate does increase, which will enhance the lung blood flow. The long oxygen levels do trigger hypoxic pulmonary vasoconstriction, which will raise the pulmonary vascular resistance. Now, as a result of doing that, it will cause the redistribution of pulmonary blood flow to perused areas of the lungs, aka parts of the lungs that are less used. Now, in doing so, it will improve the overall ventilation perfusion ratio and optimize the gas exchange within the lungs. Now, we will have acute exposure to high altitude hypoxia, which will in both the resting and the exercise cardiac output increase the oxygen delivery to peripheral tissues. Now, within the cardiac output and the oxygen uptake, they will be at the exact same level for some individuals from high altitudes as they are at normal sea levels. Now, within those individuals, they will have improved oxygen diffusion that may be attributed to polycythemia. Now, Patty had extensively talked about it, but we will just briefly say that polycythemia is just an increase in the red blood cell mass. And then next. Now, pulmonary hypertension will increase due to the hypoxic pulmonary vasoconstriction as a person ascends to higher altitudes. Looking at the graph on the right, we see that it has a linear relationship. So it will grow steadily with the altitude, which will be triggered by the alveolar oxygen partial pressure. So the higher the altitude, the higher the pulmonary hypertension. And next, that's it.
And what comes with the consequence of high altitude comes with physiological changes, where we have sleep disorders at high altitude, where many people experience periodical breathing. This means they alternate breathing between breathing too fast and stop breathing before short periods of time. These breathing irregularities can wake people up repeatedly, resulting in poor sleep quality. At high altitude, low oxygen triggers a response in the brain to breathe more. Even healthy climbers and travelers can be affected. This disruption in sleep leads to daytime fatigue, decreased performance, and slower acclimatization. Next slide, please. We have acute morning sickness effects as well. It's just a common condition caused by quick ascent to high altitudes without giving your body time to adjust. For example, just know as deep sea diving, when a diver comes up too fast underwater, it causes the body to have more oxygen inside their system, inside their blood, where they did not give their body enough time to decompress coming up from the water. So imagine that being vice versa. Imagine that just being high up on the mountain and you come down too fast, where you'll have some key symptoms as headaches, nausea, dizziness, shortness of breath, sleep problems, and fatigue. Then last but not least, we have chronic morning sickness, which is known as Mons disease. It's a long-term adaptation going on. It's seen in people that live in high altitude for years. Seen a YouTube video where it's high in the population of people that live in Colorado because of the high altitude. The body increases red blood cells to carry more oxygen, but too many red blood cells make the blood thicker and harder for a heart to pump. The key symptoms for this Mons disease is excessive red blood cell production, fatigue, and bluish skin or lips.
All right. Thank you. That was the end of chapter 19.